let's talk about conservation of energy. Conservation of energy, or conservation of anything, in physics is a very important concept. So conservation of energy. And remember what we're talking about from things like momentum. When we talk about conservation, that means the energy at the end, the energy of the final of the system, of a system, equals the energy initial of a system. And so whenever we're talking about conservation, doesn't matter if it's conservation of mass, conservation of momentum, conservation of charge. Conservation turns up a lot in physics. Conservation means the final amount of energy equals the initial amount of energy. The energy at the start equals the energy at the end. We're using sigma tau. So if we add up all of the energy in all of the forms, if you add up the kinetic energy, the potential energy, spring energy, any other energies, and get a number, then we're going to end up with the same amount here. Remember, energy is a scalar, so it doesn't have direction, so we just add it up. So let's do an example, and I'll show you what I mean. Conservation. We were talking about a skier before, just before over in this problem here, when we're talking potential energy. So a skier, 70 kgs, is at the top of a 120 meter high slope. Let's change the question slightly. If they ski down, and we're going to assume that there's no friction and no air resistance. I know the assumption is the mother of all foul-ups, but let's just assume at the moment, because we're dealing with this as an intellectual concept. If they ski down, what is their final velocity? It seems like quite an ask, I know, but let's draw a picture. So we have our skier up the top of our slope, okay, and it's 120 meters high, and we're going to, so the initial velocity is going to be 0. So this is going to be the before, and then after a certain amount of time, they're going to be down the bottom on their skis, hopefully zipping along. So here, height equals 120 meters. Here it equals, height equals 0 meters, because they've come down the hill. Here, the velocity equals 0. Here, well, the velocity is going to equal something non-zero. How do we know? Well, basically, there's potential energy here. There's no potential energy here. That energy must go somewhere. One way of saying conservation of energy is that classic quote, energy cannot be created or destroyed, it just changes from one form into another. So at this point, so the total energy in the system is going to be potential. As it goes down the hill, it changes into kinetic. So down here there's no potential energy. EK, and I've run out of paper. EK equals 0 joules. Here there's going to be no potential energy, but there's going to be some. So let's work out the potential energy. So at the start, EP equals mass times gravity times height, the gravitational potential energy, just like we did in this example here, equals, well, they weigh 70 kgs. Their gravity, we're going to use 10 meters per second squared just because it makes the maths easy. and we're using a height of 120 meters, and we worked that out earlier. That's 84,000 joules. So the total energy, E initial, equals, well, there's no kinetic energy, okay, unit 4,000 joules. So at the start there's 84,000 joules, nothing. E initial equals 84,000 joules. What's E final going to be? Well, from the conservation of energy, it says that the total energy, this is the total at the start, is going to equal the total energy at the end. So this is the sum. So it's going to equal 84,000 joules. So, and we've said there's no other energy losses, so we're not losing it to friction or anything. And we will do an example with friction shortly, but let's do 84,000. That means the kinetic energy, there's no potential energy, I have to subtract 0, so the total kinetic energy now is 84,000 joules. So at the top we had 84,000 joules of potential, down the bottom it's 84,000 joules of kinetic. And that leads us to EK equals half mv squared. I want to find out the velocity. What is their final velocity? I know kinetic energy, I know the mass, I can work out the velocity. Aha! So rearranging this over half, 2ak equals mv squared. V squared equals 2ek over m. That's square root of both sides. V is equal to root. Make sure to take all root sign all the way down, 2ek over m, which is equal to root 2 times 84,000 joules all over 70 kg. This is what calculators were invented for. 2 times 84,000 divided by 70 equals, take the root of that, equals 48.99 meters per second. Let's call it 49 meters per second. So two significant figures. Okay. So that means down here velocity equals 49 meters per second. So up here they had zero velocity. As they go down the hill they picked up speed, and if any of you have ever ridden a bicycle or on roller skates or skied, you'll know this is true. As you go down the hill you get faster. So we'll do another example, we'll do a harder example with a bit of friction shortly, but the big point is with this type of exercise you end up all of the energy at the start, all the types, whether it be potential or kinetic or whatever, and that's going to equal the total energy at the end.